Okay, our next presentation in this showcase, and I should have mentioned as well, this is a showcase of best practices is what this is. So these were the 3 best of the 9 that the executive committee voted on. This presentation is a parallelized cartographic modeling language-based solution for Flux footprint modeling. We heard a little bit about this before. Michael Hodgson, who told us a little bit about it before, will tell us more about it now, and then Jan Louis will join him after.
Thanks, Tim. I appreciate your attention, and what I'll do in the interest of time is shorten some of the things that I said yesterday, and I'll expand upon a couple of things that I didn't say yesterday, of one of which Mary pointed out to me last night at dinner and says, why didn't you show them a map of the results? Okay. And so I didn't really want to show you that yesterday, but anyway, it is here today. This is the Flux footprint. This is a probability surface of the likelihood of air parcels coming during that 12-hour period from different locations on the landscape. The higher red values mean the probability is greater there. And so what this suggests to us is that there probably was an effluent source there, perhaps burning of sugar cane, where the ammonia would be coming to the receptor location here. But it also suggests some other things, that the 1D model we've got may have some issues involved with it. And the interesting, we haven't really talked about this much in the context of the discussion, but the labor involved in actually constructing a model and verifying that it actually is working, it takes a lot of computing resources when you have big data sets. And so once we get the model run, that's fine, once it's verified, but even getting to that stage takes quite a bit of effort. I've had the fortune of working in a community called the hazards community for a long time, and over the years it's taken different realizations, one of which was in the Department of Energy's interest. You know, they're interested in a lot of things, weapons of mass destruction, and part of that process was creating a lot of things that they discarded. And some of my life was involved with trying to find those things that were discarded in the landscape. Since '89, I've been involved in looking at natural hazards. It was the dual hazards in 1989 of Loma Prieta and Hurricane Hugo. I was in Puerto Rico actually for Hugo, and then I went to Santa Clara County for Loma Prieta. And over the years, I'm becoming more and more involved in the hazard response community. The last 10 years pretty much has been hazard response. And I will make one comment about hazard response, that 3-day window of opportunity that the emergency response community is really interested in, and the high performance computing interest. And that is time, I think, really is important. It is important to certain domains. More so than many other things. And I'll use one example that's often told me by my colleague at DHS Science and Technology. He says, Mike, he says, you know, most of the people in the field, the USAR guys, the fire department, he says, they'll always tell us, give me 80% of the answer now, as opposed to 100% of the answer 3 days from now. Because I've got other sources of finding the answer if you can't tell me now. So time is really important. I do want to say one other thing. I've had the pleasure of working with 4 of Shao and Wynn's graduate students over the last year, and it's just been such a sheer joy. They're as excited, or probably more so than I, about this technology. And you see them walking around, you know, Paul just, you know, the guys who just hang in the microphones on it, these are all graduate students doing fantastic research, you know. And so I get excited about and stimulated just being involved with them. So yeah, let's give them a hand. Okay. One comment about the interest here. I'm going to talk a little bit about why we care about footprint modeling. I'll place it in the context of remote sensing. If you're a remote sensor, you'll understand what I mean by a footprint. I'll also tell you something I don't have in the slides in here. DHS is interested in this as well. Why? Because there could be atmospheric releases of anthropogenic origins, and they want to know where it's coming from, and they need to know it real fast. Okay, here's the receptor location for this study site that my colleague April Hiscox is working on, and she wants to be able to model where that effluent is coming from so she can correlate it with her ammonia samples. 3 questions up here. Where are the sources? What are the sources of observed air samples? That means where. In this case, we're looking at ammonia per se. Secondly, in what proportions are the source contributions? So we may know that part of the air sample is coming from one location, part of it's from another, but what relative proportions are those samples coming from? They could be coming from burning sugarcane, they could be coming from feedlots, or other kinds of anthropogenic activities, or natural activity. And then, one of the things that Mike Goodchild mentioned several times yesterday is what's the level of uncertainty of each of the sources? We need to know that from a management perspective. This is the context for this work for the U.S. Department of Agriculture, is they want to know who's contributing to these atmospheric releases, and ultimately that will play into regulations. Location of the tower here, and some of the, a little bit about the instruments. There's continuous monitoring of this location. 12-hour concentrations of ammonia ions, daytime and nighttime. Wind speed and direction are collected at 10 hertz. You might ask, why such a fast rate? They're looking at flux of atmospheric constituents. The atmospheric micrometeorologists feel like they need that. Temperature and relative humidity, and then net radiation. The instruments that they have there, a wind vane, 2 different heights and 3D sonic anemometers, 2 heights, and the denuders. I didn't know what a denuder was until I started working with April. I thought it meant other things, but it's ammonia, 2 heights there as well. Okay? Expensive to do the ammonia stuff. Ammonia samples over a 12-hour period, and we know that during that 12-hour period, the air packets are coming from different locations, and so we want to know where they're coming from. When she posed this problem to me, it was after we visited, or actually right before we visited Oak Ridge National Lab last time, and she came to me with it's a pretty big data demand. And right when we went to Oak Ridge, I met Yan Liu, and Yan said, "Wow, this is pretty cool. This is a good problem." I'm looking at it as we can't do it, and Yan's looking at, give me some more data, big data. Okay, so anyway, we started down that road. A little bit about footprint, so you know what it is. Footprint models are used in the micrometeorological community to determine what the atmospheric sensor sees. They use that terminology. What does it see? The sensor that they're collecting other information from. And the best analogy of that is the field of view in airborne or satellite remote sensing. Okay, we have a camera or sensor system that's pointed on, usually on the surface of the Earth, and we're looking at what that sensor sees. And so the analogy in remote sensing and what my colleague does in micrometeorology is very, very similar, except the time domains are much different. Okay? Time domains for the micrometeorological community, she's got a 12-hour concentration, and the atmospheric constituents coming from different sources over that period of time. In airborne or satellite remote sensing, we measure on the order of nanoseconds the time domain for the electromagnetic energy coming back to the receiver. And most of it's coming out from a field of view. It's not squares, rectangles. We've modeled it with a modulation transfer function, much like a Gaussian function here. Here's our model that we're using. This is a one-dimensional model. I'll kind of tie this up in a second about one dimension. It's pretty simple. It's a Gaussian form. But we do this for every single tenth of a second over time. Okay? And so when I worked with my colleague on that, I said, sure, we can do that with cartographic modeling language. In fact, I said, one of my graduate students in the course can do that. And Sarah Fletcher was one of my students. She came to Oak Ridge with 3 other graduate students and met Shawan students, and there was a synthesis of minds there, and so they walked away saying, okay, let's do this in cartographic modeling language, we'll pass it off to Shawan's team, and they'll be able to implement it, okay? So, cartographic modeling language. Now, again, I'm going to say this again. I think it's a great modeling language, particularly for the environmental science community, the physical science community, maybe or maybe not for some of the human applications that are more driven towards vector data models. The CML really is set up for raster modeling applications, although Tom would argue differently. But it is widely accepted, it's widely implemented, it's what we actually teach our students in the environmental modeling classes that we provide. Okay, so I wanted to put this in, okay, because, I mean, Shawan knows it. I was working on supercomputers back in the early 90s at Oak Ridge, and we had the Paragon. It was the fastest in the world at the time, except I couldn't program it. I didn't know how. I've written lots of code. I was, like Lynn and I were talking last night, we used to write PL1 code, okay? I don't know why we did that, but I'm a pretty good programmer, but I didn't have the energy to get up to speed to start writing code for the Paragon or the SP2, okay? So I had to work with a team of people there which are like Shawan's people, okay? They're really highly energetic and they're intelligent. For me, if I was going to approach this, or my students were going to approach this, we needed the software, okay? And that means the operators, the models, if they're in that form, or the user interface and the user experience, okay? my observation, the model that I want, in this case, the footprint model, it doesn't exist in an HPC form. Okay? I can't go and pull it off the shelf. It's not on the gateway. Okay? And I can tell you, I go through this 10 times a year, the model that I want to use, it's not in the gateway. It's nowhere else in a parallel form. Doesn't exist. Okay, the infrastructure, okay, another impediment. Okay, well, the gateway, and I put in quotes here, provides the infrastructure. We went over to see Blue Waters today. It was kind of cool, wasn't it? Back in the back of the room, there's another smaller box of computers, and Bayback pointed out, well, that's what we use. That's the Ember, the Silicon Graphics, 384 cores. That's the one that we use for this project back there. To the extent that the gateway has access to those computers, it's kind of like being in the cloud. I don't know where it's at, but it happens. Okay, well, that's a solution. For as long as Shawan and the University of Illinois allows the gateway to provide that to us. So that could be, the infrastructure could be already there for people like me and other scientists. The knowledge and community we've talked a lot about. I'm just going to make one up. My knowledge from the early 90s is outdated. Okay? And I learned this quickly the other night when I was visiting with Shawan and 3 of his students. Okay, so those are barriers for any of us to be involved in the CyberGIS called high performance computing. I suspect you may fall in some of those categories as well. Okay, I'm arguing that if I can write my model in a cartographic modeling language form, today it would be Python, would be the implementation. If I could write it in the cartographic modeling language form, I could verify it with small data sets on my computer, and then I could just submit it to the gateway and it would run for a big data set for a long period of time, except it would run really, really fast. Okay? Well, that's what my vision is. Not only I could do that, but everybody else in the GI science community that works in environmental modeling applications. Well, Parallel Cartographic Modeling Language doesn't exist. I'm not quite sure what it'd look like. Not sure how much the user would have to structure his code to make it more parallel to do the domain decomposition. So how can we get there? And this is what I envision, and this has been refined in the discussions and the education that I've had working with Shawan's group over here, is that my model, in Python could be transformed into a cartographic modeling-like model in some other form. Okay, now it would be C, compile C, and it would run in parallel over. And that's actually what we've done. Okay, we've actually gone through that entire process for the footprint model in the hopes of writing some other cartographic modeling language and taking advantage, in other words, not having to write anything else, to making it run. And at this point, I'm going to pass it off to my colleague, Gan. Okay?
Thank you, Michael. I want to second Michael's appreciation on our students' work. We have 2 brilliant PhD students who have lifted UIUC team's work. They're Barbek Bahazat there and Kumars Sultani. Barbek's involved in at least 3 projects related to the high-performance computing based spatial analysis algorithms and methods. And Kumars just joined us in June, and he already produced in this project. So when we took the code from Michael, it's a Python code. Python is a good language for CML, the cartographic modeling language, because it's a familiar language to GIS users. Esri adopted that as a scripting language in ArcGIS. And Python was invented by physicists. It's a quite familiar language for us. When we do this, take the code, we are racing with time, right? In this case, we also race with time. When first code came, actually, this is an initial code that we took from South Carolina team. The initial assessment is that if for the measurement data to run 100, if you look at the bottom line, if we run 100 measurements, it took 529 seconds. Then for the whole data set, that's a 24, I'll calculate it in a 24-hour data set. It'll take 53 days. Then it's obvious a mismatch on how fast the sensor can collect data than how fast we can analyze the data. So as part of our integration process, Barbeck took the code and to do this process of performance profiling, identifying the computational bottlenecks, and finding the solutions, and verifying the results. This process is a rigorous process we defined in any of the codes we like to work on. So he took the code. At first, it was very slow. So he quickly identified some of the things that he could quickly fix. The first is, if you are not familiar with these terms, I can explain it in a very plain English way. So in temporal dimension, you want to split up into different processors. That's a big long for loop. Inside of the loop, you do the loop-related things. But if you have something irrelevant, we call it loop invariant. You move that out, and it saves a lot of computation. The second thing we did was that you have to use a lot of intermediate variables in the loop. It's not a big deal if the variable is an integer, but if the variable is a big raster, big matrix, that becomes a potential I/O bottleneck, because you have to consider the I/O between the memory and the I/O if the memory doesn't hold that much data. So that part, we optimized that by carrying out, by reducing the number of intermediate variables in the loop. We also did a two-dimensional parallelization on the individual CML operators. Mainly, if you are familiar with CML, there are three types of operators: local, focal, zonal. In this particular case, it has local and focal. We parallelized two of the focal operators that deals with spatial data. And temporal-wise, it's a very straightforward temporal decomposition onto different processors. And we actually encapsulated the parallelization code of the operators, the two operators, into a Python library, such that the user's Python code, the CML code, doesn't need any modification. It's just linked to our high-performance operator libraries. And through this process, we'd like to establish the first principles or basic principles for further development, because we realize that CML program execution can be really complex, and each individual operator, depending on the type of computation it needs and the spatial data characteristics in it, it could be very computationally intensive. But through this process, I would like to get a first-hand experience on how to optimize the performance of CML code. So Barbeck did some optimization. This is what the first stage experienced. I'll introduce some of the road bumps we experienced and share the experience with you on how to resolve them. So he did the parallelization, he did the optimization. This goes down to, in Python, he had to use the reduce the data size. That's 1/10 of the original data size. This performance, you can see that the execution time goes down as we use more processor cores. And the parallel Python library we used is called multiprocessing. So I think for the performance curve, you can see it's quite impressive. But, well, that's only a small data set. And even if you look at it for one processor core, it takes about five hours to finish. That's not acceptable for running this 24-hour data. If you look at the long tail, that's because of the data size is too small. That's why Barbeck came to me and asked, can you get a bigger data set so that I can try more cores with more memory? So now we try this 24-hour data. With on this diagram, it's a 16 processor cores. It's on the shared memory machine in NCSA. This machine has 2 terabyte memory and 384 processor cores. The immediate problem, he found that the load imbalance, because when we do this decomposition and we send the workload to each individual processor core, some processor finishes the work earlier. Then it just waits for other processors to be finished. As we may on Monday talked about, the turnaround time of a parallel code depends on the slowest process. So Barback designed a dynamic scheduling mechanism using a queue data structure to actually make sure every processor is kept busy. So then that resolved the scaling issue, as you see for the blue line. So far, Barback did what he could do on Python to parallelize it, improve the performance, but we still a long way to go, because processing this many data set, it still takes a lot of time if you look at the curve. So we then sit back and thought, well, maybe it's because of the scripting language, its efficiency that affected the overall performance. At this time, QMARS joined us. So let's shift the work to QMARS, because Barback has other projects to deal with. So we thought, okay, let's implement it in C, which is very close to it's a compiled code. And the OpenMP, it seems a straightforward choice. It's equivalent to the, not equivalent, but it's even more straightforward programming. So this is I already skipped the other optimizations we did and a lot of programming profiling work they have done. So this is the end result we got. So if you look at the number of cores, that's the left column. In the middle, that's the Python implementation. It's a number in seconds. And we implemented C with OpenMP, and the whole data set, this 24-hour data set, actually the execution time got tailed down to only 251 seconds. And scalability-wise, it's scaling well, especially from using one processor to using 10 processors, 8 processors. The flat line there, actually you actually see the speed up, but I probably should have projected in log scale. You'll see better. It's not actually flat. So this is a table to show that originally for 100 records it took this many seconds to finish. Now we're dealing with 24-hour data with 864,000 records, and it only takes about 4 minutes, a little bit over 4 minutes. And we verified the load balance by looking at each core's execution time. Well, so up to this point, we seem to solve this bottleneck problem for computation for this case. And then we wrapped up our parallelization work on the parallel CML operators, specifically on the focal distance and the focal direction, and wrap that into a Python library. I'll skip this because I'm going to give you a live demo on that. For this individual operators, this is the performance. This is for the Euclidean distance calculation based on different size of the raster. As you can see, the green one has the biggest data size. It's actually, it takes 16 gigabyte of my memory. If you know OpenMP, you understand this curve. The similar curve on the direction operator. So now back to the parallel CML operator. I'm going to give you a demo. This is my laptop. It has 4 cores. And there's the CML, DIR, DIST, that's the Python implementation of the operators. If I quickly look at it, it implements a distance calculation and direction calculation as a function, and I just do the calculation on 1000 by 1000 raster. So if I run it, and I'll put a timer on it, it takes about 10 seconds for 1000 by 1000 raster. Come on. Yeah, so 12 seconds. Now, we developed this we got a high performance CML operator. In this, the script is the same. So it's from the user. If I look at it, these are the two operators, the same here, but we linked to our library. Nothing should be changed by the user, but if I run it, using one core, now you watch this place. This shows the business of my laptop's cores. So you see a hike over here that uses one core. And at the time, remember the data size is 100 times larger. And at the time it took, it's actually, it's 10 times faster, I think. If I use 2 cores, we get an even better performance. Now here you see 2 lines up. And if I use 4 cores, all of the cores on this laptop have been used. And now the performance actually got half compared to using 1 core. So this is basically the process and the experience we gained in this project. I'll quickly I'll quickly wrap up. There's some line of future work for them. For Michael's research, I can only read off the lines, so I'll just skip it. For our team's work, we realized that there can be very much computationally intensive operators in this CML, because it's a generic way to combine and reuse the raster-based processing methods. You define that as a focal, zonal, local, but it's raster-based processing. Depending on how spatial data is distributed, you can implement it in a very efficient way by leveraging high-performance computing. So one theory that's Sharon's active research area is to use the computational intensity map to analyze these things for those operators that need high-performance computing. And we're concerned we have to keep the user interface the same. If we have to expose a degree of parallelism, that should be minimum. So far, we are quite comfortable with the Python, but whether we should have a GUI-based CML program editor or something, it's up to the discussion. And remember, the CML is a way to combine the operators. So if you apply that into HPC environment, a natural question you ask would be, can I run 2 operators at the same time? We actually have a good, we are actually investigating a lot of good scenarios. We can further leverage the parallelism. And also, we already implement a lot of algorithms based on the different HPC platforms. Which one to choose, which algorithm works best. That's also will be an active research area. So by that, I'll conclude the presentation. Thank you.
Thank you, Michael and Jan. A couple of questions.
Yeah, Jan, the improvement you got between the interpretive code and the compiled code was between 1 and 2 orders of magnitude. Would you say that's a generalizable statement for these, for cases similar for geospatial data like this?
It depends on the language support. If the operators who I just showed are already included in the Python library, they actually are implemented in C. So you'll see no difference in performance. But like CML operators, these focal operators, you have to code in Python. That affects the performance because the interpreter has to interpret the function in order to run it. So answer is depends.
Can I make a couple of quick comments? The first one is maybe Ian has made this clear, but in case not, the final demo here showed well connects back to what the vision put forward at the beginning by Michael. That is the operators hidden behind the Python script, which was the improved native C language version. So the users experience the improved performance, but don't have to deal with the back-end complexity of engaging the native language of like C language, which is much better suited for HPC environment. So his demo there, I think, is very remarkable to show this vision, in fact, is in action. What was the second one? I forgot. Sorry.
Any other questions?
I guess I was just curious to sort of tie this back to one of the keynotes yesterday morning when he was talking about providing sort of the foundational pieces for the science. If I understand what you're saying correctly, you're suggesting that you're building an implementation for a high-level geospatial language, and the underlying implementation could run across different architectures in different languages, but the user experience would be, for example, a Python-based cartographic modeling language, and the end user of that would write in this Python-based CML and wouldn't need to care whether or not it ran in a GPU or in Hadoop or in Blue Waters or whatever. Is that correct?
Yeah, I can answer this question from two aspects. The first is that currently we don't know whether user need to be exposed with the details of parallel computing. If yes, how much? That's a question we don't have answer yet. Secondly, whether this implementation will send this user code to a GPU platform or shared memory or cluster computing, that's actually an active research area in computer science called domain-specific language. That captures the underlying implementation and the primitives that can be abstracted out for end users. So that's actually Barbeck and QMARS are looking at.
Brad?
Question, when I saw 128 nodes on OpenMP, were you on some large shared memory machine?
Yeah, I just mentioned it has 2 terabyte memory, 384 cores each system. Actually, Amber has 3 systems of such. And it's a shared, it's a distributed shared memory machine. We do need to work more on the further performance improvement by leveraging the memory locality to the processor cores. But the curve itself, yes, we're using that big memory machine.
Lynn will have the last question.
Yeah, just a comment, really. It looks like, okay, you got the viewshed application, which was operated. Now you've got some cartographic modeling language, and there are all these other operators that work with GIS data. So are you in the process of building CyberGIS of all of those kinds of functions?
Yeah, thank you. Actually, that's one of the slides I put there, and Xiaowen asked me to think about it. Yeah, I think, yes. For example, for focal operators in CML, you can define the neighborhood not only as the k-nearest neighbor or fixed sliding window or adaptive sliding window. You can define neighborhood as the visible area. That way, the viewshed analysis has to be carried together with this other operators of this focal for this focal operator. Then the question is, how do you choose the platform to run them? Is it possible to run them independently so that it can be executed simultaneously? Okay, thank you.
Just before Xiaowen, we'll have Michael, then Xiaowen will have the last word. or whoever answers Xiaowen's question.
I just want to make a comment on Lynn's response to Lynn's comment. I think that's an extremely important question. You know, it's an important question with whatever we or they or whoever's involved in high performance computing, what things they want to put their energy into implementing. Okay, and my contention is that if we start out with the fundamental operators, most of the other operators can be built off of them. In fact, I forgot, Mike, how many operators are in ArcGIS, 800 or 600, something like that. So a lot of those are built up off of the other pieces. Okay? And so a lot of things that we do, particularly environmental modeling and the physical sciences, are to use those little pieces. Okay? You use the algebraic pieces and you build them up. Use the statistical pieces and you build them up. Okay? So I think we open up the ability for other individuals to design their custom model in the language that they're comfortable with and execute it on high performance computing without waiting for Yan to implement widget X, you know, some distant future. So, yeah.
Okay, Xiaowen.
Yeah, I remember my second comment was it's going to be more interesting and exciting as we think of linking the operators together in terms of the computational challenges and the scalability. The cases demoed here is mostly focusing on the single operators. So I just want to point out as something even more exciting and interesting. The comment I had to Lynn was, as a project PI, try not to be biased. I listened to the community to tell me what are the exciting challenges and the research opportunities we should pursue as a project. But to me, this is amazingly exciting. I think we made a lot of progress over the last year. From the last year's conference at Oak Ridge, we learned through interactions with Michael's team. This was clearly something we were fired up for. Thank you.
When I saw Jan put up some code up there, I go, 25 years ago. This is people in a presentation showing exactly how this algorithm was done. And I go, well, here's the opportunity to redo GIS with a brand new understanding of GI science. So with that, I want to help me thank the speakers, all of the speakers, please.